Okay, in this video we're going to continue talking about the trigonometric functions in terms of the point on the unit circle if you move around a distance t. Now we're not talking about angles or right triangles or any of that stuff. We're talking about these trigonometric functions in terms of a real number t. The reason why we're doing that is because we're going to look at the graphs of these trigonometric functions as functions of real numbers, just like polynomial functions and rational functions and so on. Okay, let's ask this question. Well, what if you don't have one of those special points we're looking at last time? What if you have this point? How would you find the trigonometric functions of t? Well, sine, cosine, and tangent. First of all, let's draw the picture here. We're over here, aren't we, in the fourth quadrant? So I guess the question is, well, is t positive? Is it a counterclockwise t, or is it a negative, a clockwise t? And the answer is, it doesn't make any difference. The only thing that's important when you talk about the trig functions is the point where you end up. Anyway, that turns out to be important later. So therefore, the cosine is the x-coordinate, the sine is the y-coordinate, and the tangent would be the reciprocal. I should say it's sine over cosine, which if you simplify it becomes negative radical 2 over 2. Okay, the next thing I want to talk about, I want to go back and talk about some properties of these 6 trig functions. I want to revisit the idea of domain and also look at the even and odd properties. Sine and cosine are easy. The domain of those is all real numbers. And the reason is, if you think of t as a distance, remember it's a real number distance around the unit circle, no matter how many times you go in the positive direction or the negative direction, you're going to always end up at a point on the unit circle. It'll always have an x and y coordinate. So the domain of sine and cosine is all real numbers. Furthermore, if you look at this picture here, suppose t is, let's say, a positive distance. So you end up at this point, cosine t, sine t. And now if you go the same distance in the clockwise sense, a negative distance, this would have to be cosine of negative t, sine of negative t. Well, what is the relationship between this point and this point? They're not equal. Sine of negative t is the opposite of sine of t, which is precisely the definition of an odd function. Whereas the cosine of negative t is the same as cosine of t. That's precisely the definition of an even function. So next section, when we graph these trig functions, you're going to find that the sine function is going to be symmetric with respect to the origin, and the cosine function is going to be symmetric with respect to the y-axis. Now, getting back to the domain for a second, the tangent has a problem, right? The tangent is not defined wherever x equals 0. X equals 0 along the y-axis, doesn't it? So my question is, what values of t would that correspond to? Well, look, pi over 2 would do it, 3 pi over 2 would do it, 5 pi over 2, and so on, or negative pi over 2. As long as you have a pi over 2 involved, then you're on the y-axis, and that's what this says. This is a fancy way of saying you end up on the y-axis. N should be an integer here. Actually, t cannot equal pi over 2 plus n pi, where n is any integer, because that puts you on the y-axis. We'll see in class, though, that tangent, since it's the quotient of an odd function divided by an even function, that it'll always be odd. Then tangent's an odd function. Now the cosecant is 1 over the sine, right? In other words, if the sine of t is y, the cosecant is 1 over y. That means it's not defined wherever the y-coordinate is 0, and that's when you're on the x-axis. So what value of t puts you on the x-axis? The answer is t could be 0, t could be pi, 2 pi. Whenever you have an integer multiple of pi, you end up on the x-axis. So the cosecant is not defined. But the cosecant is the reciprocal of the sine function, and we'll show in class that the reciprocal of an odd function is an odd function. Now, how about secant? Secant equals 1 over x. So whenever x is 0, secant is not defined. Again, isn't that when you're on the y-axis? So the domain of secant, t cannot equal pi over 2 plus n pi. And since it's the reciprocal of the cosine function, we find that the secant function is also even. Alright, the cotangent is x over y. Again, whenever y equals 0, which would be, that's when you're on the x-axis, right? So here you can't equal n pi, otherwise the cotangent is not defined. However, the cotangent is the reciprocal of the tangent, which is odd, so the reciprocal of an odd function turns out to be odd. Okay, let's look at these two problems. I want you to determine whether the functions are even, odd, or neither. The way you do that is you look at f of negative x, right? So you plug in negative x in this first one. This first one says secant of x times the tangent of x. When you plug in negative x, you get secant negative x times the tangent of negative x. Secant of negative x, isn't that an even function? So secant negative x is secant, tangent's odd. So the negative factors out of the tangent. If you put it out front, you get negative f of x, which shows that this is an odd function. Whereas over here, you actually have the cosine of the tangent. That's a composition of functions. So when you look at f of negative x here, it's the cosine of tangent negative x. Tangent's odd, so this becomes negative tangent of x inside. Cosine of negative something, since cosine is even, just becomes cosine of that something. So I've proven that this is an even function, isn't it? Nice. Okay, the last thing I want to do is look at what are called the fundamental identities. These are equations that are true for all values of t for which they're defined, and they're going to become very important this quarter. Not as much in this chapter, but in the other chapters they become really important. Anyway, going back to the definitions. It shouldn't be too surprising then that the first types are called the reciprocal identities that follow directly from the definition. Okay, so this isn't hard. I wouldn't worry about this because if you know the definition, you have these already. This just says the cosecant of t is 1 over the sine of t. Well, it is. Look, the sine of t is y. The cosecant of t is 1 over y. So that's all it's saying. The second one says the secant of t is 1 over the cosine of t. Well, yeah, cosine of t equals x, secant of t is 1 over x. The third one says the cotangent of t is 1 over the tangent of t. Same thing. The tangent's y over x, cotangent's x over y. They're reciprocals. That's why they're called reciprocal identities. Furthermore, two more things here. The tangent of t is y over x, but y is the sine, x is the cosine, so this just says the tangent of t is sine of t over cosine of t. Cotangent of t is x over y, but x is the cosine, y is the sine, so cotangent of t is cosine t over sine of t. Okay, these last ones I want to talk about are called the Pythagorean identities. We'll see why they're called that in just a second. The first one says that sine squared t plus cosine squared t equals 1. Let me talk a little bit about some notation here for just a minute. When you see sine squared of t, it means sine of t quantity squared. And same is true with cosine squared of t, it means cosine of t quantity squared. So what this first one says, since the sine of t is y, and the cosine of t is x, this just says y squared plus x squared equals 1, or x squared plus y squared equals 1. Which makes sense because you're on the unit circle, right? In fact, if you think about this point xy being on the unit circle, this is the x-coordinate, this is the y-coordinate, as long as you're in the first quadrant. Isn't it true, if you think about this right triangle here, the Pythagorean theorem applies, x squared plus y squared equals 1. So really, this is just another way of saying that. That's why they're called the Pythagorean identities. Now the other two follow from the first. Let me show you how we get the other two. Again, you don't have to memorize these, you can just quickly derive them. If you take this equation and you divide both sides by cosine squared, look what you get. Sine squared over cosine squared becomes tangent squared. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. So this second one is obtained from the first one by just dividing both sides by cosine squared. Similarly, you can check this, but if you take this first equation and you divide both sides by sine squared, you get this third equation. Anyway, these do come up quite a bit, so you got to learn these. Okay, one last thing. Let's look at this problem here. Find the values of the trigonometric functions given that the tangent of t is 3 and the sine is negative. Okay, well, what quadrant are you in? Tangent's positive, sine is negative. Don't you have to be in quadrant 3? Okay. Secondly, if you were to use this trig identity here, you know the tangent, you could find the secant, right? So you plug in 3 for the tangent. Now the secant squared equals 10. But when you take the square root, since we're in the third quadrant, the secant would be negative square root of 10. The cosine would be the reciprocal of that, so now we've got the cosine. If you rationalize, you get this, negative square root of 10 over 10. And then furthermore, the way you finish this problem, there's several ways. One of them is to note the tangent's the sine over the cosine. So if you solve this for sine of t equals cosine of t, which we just computed, times the tangent. So then the sine of t becomes negative 3 square root of 10 over 10. And lastly, the cosecant would be the reciprocal of the sine. There's other ways to do it as well. Alright, we'll see you later. Bye-bye.